Good morning, everybody. Hopefully you've all had a good night's rest, and we are delighted that you are back this morning. We have another amazing day ahead of us. First of all, let me introduce our first guest here to speak with us today. And one is named Humphrey Hoppy Price, and I made sure I could call him that, Hoppy. He has been the chief engineer of NASA's robotic Mars exploration program. He was the architect of the JPL minimal architecture for humans to Mars, and has been or was the project system engineer for the Grail mission to map the gravity field of the moon, and the configuration engineer for the Cassini-Saturn orbiter mission. What a slacker, right? It's like, so an amazing, amazing human pushing us towards all manner of exploration. Joining him this morning is Paul Wooster. He is the principal Mars development engineer at SpaceX. I believe he's been with SpaceX since 2007. He's been engaged in a number of endeavors to support this goal. And currently, and primarily, he is working on the Dragon spacecraft to send cargo and humans into space. He's also looking at opportunities towards giving some open source concepts towards space activities. You guys are going to enjoy these folks so very much. And to prove what a good person Paul is, I had a kid email me this morning. Their school apparently is working on a Mars project, asking me about how animals, could go to Mars. And funny enough, Paul, he was at one point in support of NASA's vision for space exploration, managing the Mars Gravity Biosatellite, a mission to study the effects of Mars-level gravity on mammals. So I might get Paul to send the kid back an email this morning. So without further ado, please welcome Hoppy and Paul to the stage. Come on out, guys.
Thank you, Janet.
Thank you.
Thank you.
All right, so I'm going to stand up here, and I'll start off talking about extensibility from the moon to Mars. This was a topic that was covered a lot yesterday. Thank you, Paul.
You're welcome.
Let's see. That one. Okay, so first let me talk about the proposed NASA lunar architecture elements. There are a number of vehicles that get aggregated at the gateway, and vehicle assembly, operations, and maneuvering, of course, is a big feature of the lunar architecture, and also for all of the Mars architectures that I've seen, this is an important capability to verify and validate. So this is a good feed forward to Mars exploration. There are a number of vehicles I want to point out. There's the Orion capsule, the transfer vehicle element to transfer vehicles from the gateway orbit to the low lunar orbit, the gateway habitat, which is like the command module, and the power and propulsion element, which is a 50 kilowatt solar electric propulsion tug, which is like the service module of the gateway. And then there's the lunar ascent element. So NASA has a Mars architecture concept that's used as a reference, and the lunar orbiting gateway would be used as an assembly point for that. The crew would get from the gateway to Mars and back with the reusable deep space transport, and that's a 500 kilowatt class SEPTUG, so it's a step up by about a factor of 10 from the power and propulsion element on the gateway, but that's still a good pathfinder for that. The landers would be separately delivered to high Mars orbit by the SEPTUGs, as you can see in the image in the upper right-hand corner. Astronauts would transfer from the deep space transport to the lander, and the lander has an inflatable heat shield. It lands on the surface, and the liquid oxygen propellant for the ascent vehicle would be produced from the Martian atmosphere, and you can see these large radiators that are deployed to radiate the heat from that process, and there's also a lot of power that's required to generate that propellant. So there is definitely feed forward from the lunar architecture to the NASA Mars architecture. The gateway habitat and the life support components feed forward to the habitat for the transport. The power and propulsion element is a good feed forward to the SEPTUG, and the lunar ascent crew cabin hopefully could be feed forward in a big way to the crew cabin on the Mars lander. And of course, the vehicle assembly operations and maneuvering are a big part to prove out and to feed forward there. Now, yesterday, Joe Cassidy talked about the Achieving Mars Community Architecture. So I want to talk about some of these architectures and how these might also be a feed forward from the lunar architecture. There's the Group 1, the Sortie class missions, Group 2, the research station, which is similar to the reference NASA architecture that I was just talking about, and then Group 3, which is a permanent presence. So if you look at your program for the Humans to Mars Summit and you look at the back, there's a beautiful picture of Mars and it says 2033. So the question is, could we send crews to land on Mars in 2033 if we land crews on the Moon in 2024? And there's the recent STIPI report, which outlines these risks, which may not make it possible to develop all of these things in time for 2033. But I wanted to talk about the Affording Mars Group 1 concept because that would actually utilize more near-term technology systems and avoid a lot of the risks that were cited in the STIPI report. So it does not use the 500 kilowatt SEP system. It's a 100 kilowatt class SEP. It does not use cryogenic propellants. It doesn't have refueling and reusability. Doesn't have ISRU propellant production. So these are all wonderful things that we would want to have. But in this example of an architecture, they would be on-ramped later. So this would minimize the number of new vehicle developments and minimize the risk with less complex systems. But it would be evolvable to later on do all these things that we'd like to do, like ISRU. So this example of an architecture could possibly support a short stay landing in 2033. And 2033 is an interesting opportunity because it's possible to do a 570-day total mission duration if you have more propulsion to bring the crew back. So I'll talk about the feed forward there. The gateway habitat from the Moon would feed forward into the Transhab. Interestingly, the transfer vehicle element is a pretty good fit for what is used in this architecture as the chemical stages for Mars orbit insertion and trans-Earth injection. And again, the lunar ascent crew cabin could be used hopefully very, very similarly to the crew cabin in the Mars vehicle. And then this example of a lander uses the same kind of technology that's in the Mars 2020 mission. And so there's a picture there of the Mars 2020 vehicle, and it's to the same scale as the Mars lander. So the Mars lander is about a little bit more than twice the diameter of that, but it's the same kind of construction. And then, as was talked about yesterday, the lunar cargo and surface elements could have extensibility to follow on long surface stay Mars missions, like small pressurized rover, the cargo mobility systems, the cargo container systems, surface power like the kilopower system and Stirling RTGs, and also the surface habitat. So these are examples of follow-on missions with the Group 1 architecture to have longer stay. So just quickly walking through the architecture for the Group 1 concept. First, a commercial vehicle would deliver a SEP tug and a boost stage to Mars orbit, and then that would aerobrake down to low Mars orbit. And this is actually a transfer stage, very similar to what's used at the Moon to transfer from low Mars orbit to high Mars orbit. Then a 75-ton capsule lander would be delivered by SLS to high Earth orbit. Then there would be another SLS launch with no payload, but it would use the exploration upper stage as a departure stage to send the lander to Mars. Since the lander has a heat shield, it could conveniently use that to aero capture into Mars orbit, and then we have the lander there. And now we just have to get the crew there. So the third SLS launch would send the whole crew transport stack into low Earth orbit. And then another SLS launch would use the exploration upper stage to boost that to high Earth orbit. And now you're pretty much all ready to go to Mars. You've got a boost stage in Mars orbit. You've got a lander in Mars orbit. You've got this departure stack ready to go. We would use commercial deliveries in this example to send an Earth departure stage up. And then finally, the crew would go up in Orion. That would be the last SLS launch. And the Earth departure stage would send it off to Mars. It's a 200-day transit. The crew could transfer into the lander, land on the surface, spend a couple of weeks there for this first mission, and then use the map to get to low Mars orbit. And similar to the lunar concept, it would use a boost stage to transfer back up to high Mars orbit to get to the return stack. And then the trans-Earth injection stage would send the crew back to the Earth, and they would enter in the Orion capsule. So they would have to spend 550 days in Mars orbit for the long duration mission, even though they would only have 2 weeks on the surface. So what would be interesting is to take advantage of the 2033 opportunity for a short stay mission. And what you see I've added on the left is another SLS launch with another stage, because it takes more delta V to get back from Mars for the short stay concept. And also there's a Venus flyby that's been added, because you have to get a Venus gravity assist on the way back. So from an engineering standpoint, this is a more difficult mission, because you have another rocket stage, you have another launch, you have to do a Venus flyby. This shows a deployable sunshade, because when you get in close to Venus, you have to protect the deep space transport and Orion from twice the solar intensity at Venus. But it's great for the crew, because it shaves about a year off of the trip time, taking advantage of the 2033 opportunity. And also, you know, this would be a great mission for the crew, because it's a short stay. They would be the first crew to land on Mars. They'd also be the first and perhaps only crew to ever go by Venus on the way back. So that would be a pretty exciting mission. And this would be a pathfinder for a continuing series of long stay missions. And in this concept, there would be a separate sky crane lander, like what we used for the Curiosity rover, to deliver an unpressurized rover, so they would be able to drive around some while they were on the surface. So it would be significantly greater in scope than Apollo 17 and be able to do some significant science. But this would just be a pathfinder for longer stay missions. So looking at a notional flight scenario, these are the SLS launches for the initial moon program, showing a 2024 moon landing and the series of EM missions to the moon. And then in this example, there would be a test of the deep space habitat. You definitely want to test that out before you commit it to this year-and-a-half long mission to Mars on the 2033 opportunity. And then this would be the first Mars landing, 2033 Mars landing, 1 to 2 week surface stay. And this would be the second Mars landing, and so that would be 4 years later, and that would be a 500-day surface stay, because we would have a surface habitat for the crew to stay on the surface. And then we don't want to forget about the moon, so we're going back to the moon to stay. So there would definitely be room for more SLS launches. If you're launching the SLS twice a year, you could do the Mars program and still have continuing missions to the moon. As was pointed out yesterday, we think it's important to have low Earth orbit flights to train the crews, and so we could still take advantage of the commercial crew capability that SpaceX and Boeing have, and that Sierra Nevada and others might eventually have for commercial crews to low Earth orbit. And then there would be continuing missions to Mars. This would be a third Mars mission, a fourth Mars mission. So they would go every 4 years, and you would continue to build up infrastructure on the surface and eventually be able to create oxygen and propellant and utilize water on Mars. So maximizing the feed forward to Mars, lunar elements could be designed to maximize this by proving out needed technologies, components, system designs, mission operations, and surface operations. And really, the mission operations and surface operations are very important to prove out before doing these missions to Mars. It would develop the vehicle assembly and maneuvering capability at the gateway to retire the risk of the Mars missions and reduce the cost and schedule for developing the Mars vehicles. And conversely, the initial Mars architecture vehicles could be designed to maximize the heritage from the lunar elements and try to use that same type of technology, realizing that later on you can on-ramp more advanced technologies with greater capability and going towards reusability. So an early crewed Mars moon landing in 2024 could serve to advance exploration vehicle development and could possibly lead to a Mars landing as early as 2033 if sufficient funding was available. And so now I'll hand over to Paul. Thanks.
Okay, thanks, Hoppy. So wanted to talk a little bit about SpaceX's overall Mars visions and plans. I will, though, start off with this picture here, just as a reminder that what SpaceX was founded in order to achieve. So SpaceX's intent, Elon's intent in founding SpaceX, was to enable humanity to become a multi-planet species, allowing us to establish cities on Mars and really allow humanity to move outwards and just help out, I think, inspiring people overall. So while some aspects of this are an artist's concept, the vehicle itself is very much in development now and something that we're looking to enable this. Overall, though, throughout the history of SpaceX, we've been, I think, building towards this vision. So, going all the way back to Falcon 1, the initial flights there, a little over 10 years ago was the first time we got that to orbit. That was really helping us learn how to launch, how to get into space, which served as the basis for other activities from there on. Getting Falcon 9 flying, our Dragon cargo missions, working very closely with NASA on the development of that, and now also on commercial crew. And then a key aspect for all of this in order to reduce the costs has also been introducing reusability to the overall launch game, and then increasing the total lift capacity. So I think one of the things that's really been exciting over the last year or so is having Falcon Heavy come online. So this was a picture of the first launch of that, and then just last month, the first operational flight, so second flight overall for Falcon Heavy. It was great seeing in Hoppy's slides there some icons that were very familiar. We're certainly quite happy to help out NASA in their overall plans for going to the moon and Mars using Falcon Heavy. This is the largest operational launch vehicle. Very, very high liftoff thrust. There you can see the Merlin engines. Just after liftoff. There. So something where we're quite excited about the capabilities this brings to bear. We have a number of missions coming up in the near future on it. A mission for the Air Force that also has a number of rideshare payloads this summer, and then further ones going forward, and something that we're quite happy to offer in support of this overall vision. Key aspect here that we've been proving out, though, is also the reuse of the first stage of Falcon. So these two side boosters coming back to land after our first Falcon Heavy flight, very spectacular coming in and landing. The other thing, though, is that these boosters had flown before, so this was not their first flight. With the Block 5 version of Falcon, now we're qualifying our first stages to fly 10 times. We've already flown 2 of them three times, and we'll be increasing that further and further. So having this reusability is allowing us to drive down the cost and also increase our overall launch cadence. Now, moving forward, so over on the left here, there's a very small person, or full-scale person, small on the chart, person for scale here. You can see the progression of the Falcon 1, which taught us how to fly into space, get orbital, and then go on with the Falcon 9, and then eventually Falcon Heavy. Now, all of that is leading towards the vehicle that we're developing currently, which is our Starship vehicle over there on the right. This is a 9-meter diameter vehicle, 118 meters tall. We have 31 Raptor engines on the first stage and 7 on the second stage in order to fly that to orbit. In this case, not only are we reusing the first stage of the vehicle, but also the second stage. So that's going to help us decrease the cost of access to space even further, such that we actually expect that the marginal cost for launch on this vehicle will be lower than our existing vehicles. That's really going to, I think, be revolutionary in terms of the capabilities that will allow us to bring to bear. So on that second stage, we basically have a heat shield along with aerodynamic surfaces to control its entry to Earth, along with propulsion systems, and then a large payload compartment that's integrated with the overall vehicle. In that payload compartment, we have over 1,000 cubic meters of volume available for crew or cargo or what have you. The way in which we make use of this vehicle, so basically it's a 2-stage fully reusable vehicle. Now, in order to go to Mars and have a very large payload capacity, we're looking at being able to deliver over 100 tons of useful payload. The key enabler beyond the low-cost launch to LEO is doing propellant transfer. So we're able to take a ship on orbit, refill it with propellant, and then basically reset the rocket equation such that we can then use that same system to go on to Mars. That basically takes a 2-stage fully reusable vehicle and effectively turns it into a much larger 3-stage vehicle from an overall performance perspective. When we get to Mars, we use the same aerodynamic deceleration systems, basically the primary heat shield and the aerodynamic surfaces, in order to allow the vehicle to slow down and stop. Between the low-cost launch and the propellant transfer, that basically allows us to do very fast transits to Mars by both having the large propellant capacity to begin with and then slowing down. For the return back, we're filling the propellant up again, in this case using local resources, water and carbon dioxide, water from the surface, carbon dioxide from the atmosphere, along with a significant amount of power to basically drive combustion in reverse back into methane and oxygen to fill the vehicle back up. Now, in doing this, we also have a very versatile system that can do many missions beyond just flying to Mars. So we can launch satellites here at Earth, and we can also do moon missions with the same vehicle by leveraging the very significant propellant capacity that it has available to go from Earth orbit to the lunar surface and then all the way back as well. So I'm going to give you an overview of some of the work that we have going on. So this is the first test firing of the flight version of our Raptor engine. We've been doing a whole series of development tests. We basically started those tests in 2016, went through 2018 with those, but now we have the flight version of this engine. So this is the same engine that will be flying on all of our vehicles. We've had basically the fourth of these flight engines is now on the test stand in Texas. We've completed testing on 3 of them already. We were very quickly able to get up the full thrust capability on these engines within the first week of the first one of these units. We were there. So we're very excited about that and working to ramp up our overall production rate on these engines to enable our overall vehicle missions to occur. In addition to testing the engine itself, we've been also working on the integration of the engines into the propulsion stage for a Starship. So this is basically a hopper vehicle that we've built at our facility in South Texas to test things out. And here's a little video of it under tethers doing its first hop. The vehicle is still there. The video kind of cuts off just because the camera had some issues. But this is a very Spartan facility that we have down the very far south end of Texas in Boca Chica. We're building this up with time. We're also creating production facilities both there in Texas and also at Cape Canaveral in Florida in order to build up the next versions of Starship, get into suborbital testing, and then onto orbital flights. So in the not too distant future, we'll be looking to have launches like this taking place, getting to orbit, proving out the overall launch capability, the capability to bring the Starship back down to Earth and reusing it as we go forward. Additionally, this vehicle opens up a number of other mission opportunities. One that we're very excited about is that we announced back in the fall was that we'll be flying a group from the Dear Moon initiative, which Mr. Meizawa from Japan set up to fly a number of artists around the moon. So this will be the first passenger flight around the moon, and by having those artists on board, I think it'll be very exciting to be able to help bring back the overall experience there to people here on Earth. And then obviously this is something that we're happy to do moving forward as well for additional customers. By having that propellant transfer capability and the large delta V that the vehicle can then achieve, we're also able to basically fill up the vehicle in Earth orbit and send it to the surface of the moon. By doing that, not only can we deliver payloads itself, but I think having that vehicle on the moon can serve as basically the core of a pretty significant lunar outpost growing with time. So just beyond the capability of delivering up to 100 tons of useful payload, having the over 1,000 cubic meters of volume in the forward section, when you combine that with the propellant tanks over 2,500 cubic meters of volume, could really help you get started quite quickly there on the surface, and something that we're quite supportive of. And then with time, looking to have something grow to much more significant lunar surface presence. And because we're using the same transportation system to both go to the moon and go to Mars, it's not something where we need to choose to do one or the other. We can actually do both. We can do them in parallel. Just like we have in Antarctica, a number of research stations, we would envision having a similar sort of setup on the surface of the moon while moving forward and going to Mars. So this is concept of the ship coming into land, which we would then eventually again build out to more of this overall city, something that can grow with time and really expand our presence beyond Earth. So I think with that, maybe we'll flip over to questions.
Yeah.
Or not.
Yeah. Does anybody have any questions? There's the microphones on the side.
Ben Pearson, Reuters Roaster. Paul, what do you consider the biggest risk to the Mars program as far as SpaceX is concerned? What's the biggest problem that you're facing right now?
So right now, I would say that we're very much focused on getting Starship flying, getting to orbit, and proving out that full reuse capability. The overall approach that we're taking in developing this system is to minimize the number of things that we need to do in order to get that first mission to Mars. So, we basically have those two stages, the booster stage, called the Super Heavy, and then the second stage, the Starship. Getting both of those flying is definitely critical for the overall mission to move forward. But there aren't many things beyond that from a transportation perspective to move forward with that. We obviously have to prove out things like landing those vehicles and the overall reuse, and then the propellant transfer, which is quite key to be able to take that two-stage fully reusable vehicle and turn it into something that can take very significant payloads to Mars. Once you start talking about having people on it, there's also going to be significant infrastructure that you'll need on the surface of Mars. I think there'll be a session later today on that topic. That said, having that large payload capability really can simplify a lot of the developments there. So for life support, as an example, we can use technologies very similar to what's on the space station, and in many ways take a brute force approach early on, and then improve that, recycling fraction and so on as we move forward.
Hi, this was for Hoppy, Joe Cassidy, Aerojet Rocketdyne.
Hey, Joe.
Hey, Hoppy. So interested to see how you pointed out there that the approach that we looked at in our AM concept did address a lot of the risks in the STIPI report. But I had one other one for you. Is not the use of the kind of traditional aeroshell approach also not another risk area that we could eliminate from a tall pole standpoint, like having to have deployable Mars entry systems? So
sure, yeah, that wasn't really outlined in the STIPI report, but definitely the HIAD, the aerodynamic decelerator that's inflatable, is a risk factor, and it does require some development. And the example that we used for the AM5 Group 1 architecture uses more of the Mars 2020 type heat shield and back shell. But interestingly enough, Glenn Research Center is planning a test flight of the HIAD in the next year or two, and so it'll be interesting to see how that works. I mean, I'm hoping it'll be very successful, and that would retire some of the risk for the HIAD. But even so, getting the technology readiness level up and getting ready for a 2033 mission might still be a challenge for that. It might be that the first landers would be more of a capsule type lander, and that the HIAD type technology could be on-ramped later, but that would be if you really wanted to do a push for a 2033 mission. If you're willing to just wait, till a later time, then you might wait until the HIAD is ready. Yeah.
Hi, Tatiana Indina, a Mission to Mars Academy Accelerator from Silicon Valley. I have a broader question. How do you envision the future of commercialization of space? And a question to SpaceX. SpaceX is a successful private company that used to be a startup. Maybe you're still a startup, but do you plan to somehow engage with smaller tech startup companies in the United States or globally? Thank you.
Yeah, I think that it's not only been SpaceX that's been enabling it, but I'm been really excited about all of the developments that have been happening in the commercialization of space, increasing the amount of activity that can occur there and the variety of activities there. So SpaceX is not just founded to go get to Mars, but enabling all of those different things has been quite exciting for us, something we've been very happy to do. I think when you look at the overall endeavor of having people on Mars, it's also going to be something where there will be a lot of opportunities across the board for people to engage in all sorts of different things. On that picture of the city on Mars, we're focused on the ship, getting things there, getting large quantities of cargo and people, but creating a city involves a lot of different activities as well.
Yeah, from the NASA standpoint, the Space Launch System will probably be limited to a couple of launches a year, at least in the time frame that we're looking at in the 2030s. So I think it's very important to us that we do have these commercial capabilities with the Falcon Heavy and the New Glenn and the Vulcan and other launchers to be able to get all the stuff we need to in the vicinity of the Gateway and also to send payloads to Mars like unpressurized rovers and transfer stages if we're going to use those at Mars. So yeah, definitely the commercial capabilities are very important.
Hi, I've been wondering what is the payload capability of the Starship compared to the SLS, and assuming it's bigger, how that might change your architecture, Hoppy, because you really have a lot of launches to make this 2033 thing happen.
Right. So, if the Starship is ready and if it has the payload support capability that we would need for these elements, then yeah, certainly I think NASA would consider using that capability. But the architecture that we showed, didn't assume that it would be ready in time. But if it is, yeah, I think we would take advantage of it. Over there.
So this is a question, I guess, mostly for Paul. But so how do you envision the SpaceX architecture? Is it compatible with the NASA architecture for 2024 moon landing and certain other things, or would it mostly be ready afterwards, so it wouldn't matter?
So we have a great relationship working with NASA. We've been partnered with them on a whole variety of different things, and we're very excited to help work with NASA on enabling the 2024 lunar mission happen. And as I said, definitely excited about helping out there any way we can.
Good morning, this is Robert Howard, NASA JSC. Questions for Paul. Hoppy just mentioned the SLS has a launch rate of 2 per year. What is your current max launch rate for Heavy? What could it grow to potentially if the market supported it? And once Starship is flying, do you plan to continue operating Heavies, or would you retire them?
So overall with Falcon and Falcon Heavy, we've been significantly ramping up our production capability and our launch rate. So in 2017, we had a total of 18 launches. Last year in 2018, 21 launches. One of the key aspects beyond having improved our production process actually is the reusability there. That allows us to increase the operational tempo without having to build a new stage each time. Falcon 9 and Falcon Heavy basically share all of the same production infrastructure, same engines and tooling and launch sites and whatnot. So we are able to flexibly move capability between those, and I don't foresee a particular constraint on our capability to support launches with those vehicles in the next several years. With Starship and Super Heavy, we're looking to be able to increase the launch rate even further beyond what we've already demonstrated with Falcon 9 and Falcon Heavy. That said, we are going to be operating both vehicles in parallel, and we'll only be shifting customers over to Starship as they're ready to do so. So, Falcon 9, Falcon Heavy definitely have a good future ahead of them as well.
Okay, thank you.
All right, Clive, you have a question?
Yes, I do. Clive Neal, University of Notre Dame. Hoppy, this one's for you. In your opening statement, you said we would do the first landing with nothing reusable, and it would be throwaway, but it would be evolvable.
Right.
And you didn't say how it would be evolvable, because my concern is you do a throwaway mission, I see flags and footprints, one and done, and canceled. How evolvable will that be, and how much more time would you need beyond 2033 to make that first mission, reusable and evolvable?
Right. So, yeah, we have looked at how the Group 1 architecture could evolve to have some significant reusability. But one of the things I'll point out is that, when you build serial number 1 of that habitat, serial number 2, serial number 3, my guess is you probably wouldn't want to refly any of those. There would be so many things you would find out after that first mission. The engineers would say, hey, wait, we got to redo this, this, and this. There's no way we're going to fly this again. So, I mean, how many flights did you have of the Falcon 9 before you were really ready to start reusing those vehicles? I mean, could you have reused the first 2 or 3 of them?
Well, I'd say we took a very iterative approach to our development, and that's something we've been doing throughout. So I think having a rapid pace of development and innovation can be helpful there, and that helps us learn how to reuse the vehicles. If you follow back on the first stage recovery efforts, there were a lot of iterations there to get that right. But now I think it's kind of a surprise for people when we aren't even trying to recover one. So definitely things have changed there, and now I think over half of our flights have involved reused boosters.
Yeah. And so for spacecraft, I mean, if you look at the Space Shuttle Columbia, the first flight, second flight, third flight, I think there were some significant changes that they needed to make to address design issues. Luckily, they had an army of people on the ground to do that. If you look at Apollo 7, 8, and 9, there are changes that they had to make to those vehicles. Of course, a big change after Apollo 13 to the fuel cell system. So, I mean, I really think that you would do a number of flights before you were just technically ready to reuse them. But for the Affording Mars architecture, since you have these SEPTUGs, the 125 kilowatt class SEPTUG, you can design it to leave a couple of tons of xenon left in there. And so we've actually worked out a trajectory where when the Deep Space Hab comes by Earth with the crew would still enter in Orion, but you could deflect the Deep Space Hab, a SEPTUG could pick it up, and you could return that Hab to reuse it. But actually, my favorite reuse of that Hab is not to send it on another mission to Mars, but I would take that Deep Space Hab and put it in low Earth orbit and use commercial crew deliveries to train crews in a real Deep Space Hab in low Earth orbit. So, besides reusability, you can also think about repurposing.
Right.
Now, reusing the Mars lander is a more difficult prospect. Of course, SpaceX and the Lockheed Martin base cap concept do have reusable landers, but again, I think you would want to fly a number of those before you would really technically be ready to be comfortable with reusing them.
Okay, all right, thank you.
Yeah, sure.
Hi.
Sure.
Good morning, Gus Sherbaum here. Both of you just said previously that you were open to future commercial opportunities, with humans to Mars, and also opportunities with 2024 going to the moon, et cetera. But given the significant need that a number of us have been discussing here about life sciences, life support, and the development of those areas, and also given the fact that NASA has had commercial opportunities for smaller startup companies in terms of developing needs, will SpaceX have similar opportunities for smaller companies to sort of advertise, we need a certain widget or whatever to create better life support for our system? Is that happening? I don't think we got a full answer before. So.
Sure. I think the work that NASA's been doing to support all of those technologies and move things forward, has been quite helpful. Something that I think would be great to continue moving in the future. In terms of SpaceX ourselves, the company is quite vertically integrated in terms of having our own in-house production capabilities for the things that are critical to our mission. But as I was saying earlier, I think there will be plenty of things that are complementary to those capabilities where all sorts of different players can have a role.
Yeah, so Paul, your life support for the Crew Dragon, that's all done in-house?
Yes, that's right. I mean, we have developed that. Now, in that context, that's a relatively short duration system, so very different from what you'd want to have for a 6-month transit to Mars. But we are able to basically use that same system for things like flights around the moon or basically things in Earth-Moon space. Moving forward, I would imagine that a lot of that will, for missions to Mars, will be leveraging capabilities that NASA has been developing over the last several years, decades, and so on. But that will be something also once you get down to the surface where you're going to want to start making use of local resources and a whole suite of technologies surrounding that as well.
Yeah, next question.
Hi, it's a question for Paul. You showed the renderings of Martian cities.
Yes.
How does SpaceX have a plan on how people might survive given the conditions of Mars in these cities, or would you be partnering with other companies to sort those things out?
So yeah, again, that's one where for the capabilities that you'll need on the surface, very excited to have others helping out there, and we want to enable that by providing that low-cost transportation service. I think once you're on the surface, there's opportunities for trying out a whole variety of different techniques, much more so than on the transport side. You can have a faster iteration cycle, also the level of integration that you need in order for something to work, I think, can be quite different. When you are initially on the surface, I would imagine that people will be basically living out of the starships to begin with, and then expanding out with local habitation and whatnot with time. Some of the key things early on, though, I think will be more accessing resources and proving out those things are available for your both return flights and building out those cities.
I think we probably have time for one more question.
Thanks for your insights, and thanks again I appreciate the Dear Moon. I mean, I think when you market the Moon and Mars, sending artists is a fantastic way. But I was going to pull on the thread of the Marco mission. So if you consider the ballast in future missions architectures, do you think there are going to be opportunities for small satellites?
Yeah, so I think Marco and Hoppy probably can speak even more to that.
It was built at JPL. Yeah.
Right. Exactly. I think that was great. These I think it was 6U CubeSats.
Yeah. 6U CubeSats with deployable high gain antennas. Yeah.
Yeah, that was great to have those flying along with the InSight lander and providing relay coverage during the critical EDL events. And I definitely see there being lots of opportunities for small satellites, CubeSats, and so on, and all this moving forward too.
Right, and so I think as we look to the future of Mars exploration, and really even lunar exploration too, I mean, there is going to be a need for communication with crews. And so just as we have a network of satellites around the Earth for communications, I think if we're really going to build cities on the Moon and Mars, then we'll need these comm satellites, and having small sats do some of those functions, I think could be quite cost effective, just as SpaceX is looking at smaller satellites now in a network around the Earth.
Right.
Yeah, so yeah, I think there's a big future for these small sats. And I think that's it.
Let's give them a big round of applause. Thank you guys so much. We've already got commercial and NASA participation and collaboration. I like it. Thank you guys.
We're buddies.
Yeah. All right. Let's go. Let's go. Thank you guys.